In this video, we're going to cover some alternative coordinate systems for Schwarzschild black holes, called the Eddington-Finkelstein Coordinates and the Kruskal-Szekeres Coordinates. These coordinate systems make it clear that light and massive particles can indeed pass through the event horizon, and they also lead to some theoretical ideas like white holes and wormholes, also called Einstein-Rosen bridges. In the previous 3 videos, we looked at the Schwarzschild metric, which is the metric for a spherically symmetric, non-rotating, uncharged mass. We defined the Schwarzschild radius Rs for a mass m as 2 mg over the speed of light squared. When an object's physical radius becomes smaller than its Schwarzschild radius, the object becomes a black hole, with Rs becoming the black hole's event horizon. We found that anything that crosses into the event horizon, including light, can never get back out, and is forced to move towards the singularity in the center. Now, one problem with the Schwarzschild metric is that it breaks at 2 locations. At the origin, r equals 0, which sends gtt to be infinite, and at the event horizon, r equals rs, which sends grr to be infinite. The infinity at the origin represents a true geometric singularity. This is a location where spacetime comes together in a pinch and our theory of general relativity stops working. But the infinity at the event horizon is just the result of a bad choice of coordinates. This is similar to how, in 2D polar coordinates, the origin is a point where derivatives no longer work and basis vectors aren't defined. We can change from polar coordinates to Cartesian coordinates to make the origin point well behaved again. And similarly, we can change from Schwarzschild coordinates to these other coordinate systems to make the event horizon well behaved. One thing to keep in mind is that the Schwarzschild spacetime geometry is not changing in this video. We're keeping the same spacetime geometry, but changing from the Schwarzschild coordinates to these other coordinate systems. Now, before I derive the Eddington-Finkelstein coordinates, I'm going to skip ahead and spend a few minutes talking about the metric in Eddington-Finkelstein coordinates. This metric looks a bit weird because it has off-diagonal components as well as a 0 on the diagonal, and this might confuse some people. If you don't need an explanation for this, you can look at the video chapters and skip ahead. So we see that the metric components in Schwarzschild coordinates and Eddington-Finkelstein coordinates are mostly the same. However, the Eddington-Finkelstein metric has some off-diagonal components. This might seem weird, but all this means is that the coordinate curves in Eddington-Finkelstein coordinates are non-orthogonal. Let's go back to boring 2D flat space, with basis vectors ex and ey. These basis vectors are orthonormal, so x.x and y.y equal 1, and x.y equals 0. And remember, the metric components are just the basis vector dot products. So in this basis, the metric tensor is the identity matrix. Now, let's create a new basis where ex tilde equals ex plus ey, and ey tilde is just ey. This basis looks weird because it's not orthogonal, but it still works perfectly fine. For example, in the first basis, this vector v equals 1 ex plus 2 ey. And in our new basis, v equals 1 ex tilde plus 1 ey tilde. We can still express vectors perfectly fine in this basis. We can also calculate the metric components. To get ex tilde dot ex tilde, we can just sub in this formula and distribute. And these dot products go to 1, 0, 1, and 1 plus 1 is 2. We can also compute ex tilde dot ey tilde to be 1, and ey tilde dot ey tilde is also 1. So given these dot products, we can see that the metric tensor in this basis has off-diagonal components, because this basis is non-orthogonal. And this is why we see off-diagonal components in the Eddington-Finkelstein metric. The time and radial coordinates are non-orthogonal. Another strange thing about the Eddington-Finkelstein coordinates is that the GRR component of the metric is 0. But this just means that the r-coordinate curves are light-light curves that match up with the paths of light beams. Remember, at any given point, a vector inside the light cone is called time-like and has positive squared length. A vector outside the light cone is called space-like and has negative squared length. And a vector right on the light cone is called light-like because it follows the path of light, or null because it has a squared length of 0. If we look at a 2D flat spacetime with a time and x basis vector, ET is time-like with a squared length of +1, EX is space-like with a squared length of -1, and ET and EX are orthogonal, so their dot product goes to 0. So our flat spacetime metric in this basis looks like this. But we could also change basis so that ET tilde equals ET and EX tilde equals ET plus EX. This means that EX tilde points diagonally along the edge of the light cone, so EX tilde is a light-like vector. Again, this might seem weird, but we can use light-like vectors in linear combinations just like any other basis vector. If we calculate the dot products ET tilde dot ET tilde equals +1, ET tilde dot EX tilde equals +1, and EX tilde dot EX tilde becomes 1 plus 0 plus -1, which equals 0. So given these dot products, the metric in this basis looks like this. It's non-orthogonal, so we have off-diagonal components, and EX is a light-like vector, so its squared length, GXX, is 0. So this Eddington-Finkelstein metric might look weird at first, but just remember the off-diagonal terms mean the coordinate system is non-orthogonal, and the 0 here means that the r-coordinate is pointing along light-like curves on light cones. Now, let's actually derive the Eddington-Finkelstein coordinates, which I'll call EF coordinates for short. The idea behind the EF coordinates is to look at a collection of light beams falling into the black hole and use these beams of light as coordinate curves for our new coordinate system. First, let's remind ourselves what the light-like geodesics are for radial light beams, whose tangent vectors d by d lambda have 0 squared length. If we set the path parameter lambda to be the r-coordinate, we end up with this differential equation whose solution looks like this, with plus for light beams going away from the black hole and minus for light beams going into the black hole. So far from the Schwarzschild radius, this log part goes to 0, and these just become diagonal lines. But close to the Schwarzschild radius, the log part blows up to infinity, and it appears as though ingoing light beams never cross the horizon. However, it should be noted that light beams and massive particles can indeed cross the event horizon. It's just that the Schwarzschild time coordinate CT measures proper time for an observer very far away from the mass. And from this distant observer's perspective, nothing ever appears to cross the event horizon due to gravitational time dilation. But when looking at an infalling observer in their own reference frame, they can cross through the event horizon just fine. Also note that this solution involves the log of an absolute value. So we get additional solutions for light beams inside the event horizon, where r is less than rs. The light beams in this region appear disconnected from the outside light beams. We can fix this by changing our time coordinate CT to a new time coordinate CT tilde by shifting CT by this logarithm term. This new time coordinate is called the advanced time coordinate. If we look at our equation for the paths of ingoing light beams and replace CT using this formula, we find that the log terms cancel. So using this new time coordinate, ingoing light beams have a slope of -1 and are diagonal everywhere, even across the event horizon. So we can see that light beams do indeed pass through the event horizon without any problems. So why did this trick work? Well, if you look at the ingoing light geodesics outside the event horizon and inside the event horizon, they appear to be disconnected. But you can loosely think of them as being connected up at infinity. This new time coordinate basically shifts time to pull these curves down, and the amount of shifting depends on r. The closer we are to the event horizon, the more shifting happens, and at r equals rs, we basically do an infinite amount of shifting to bring down the curve from infinity. So the advanced time coordinate CT tilde gives us a nice coordinate system where ingoing light-like geodesics pass through the event horizon and have a constant slope of -1. But we still haven't reached the Eddington-Finkelstein coordinates yet. For EF coordinates, we want light beams to travel along constant coordinate lines, instead of being diagonal. So instead of shifting the time coordinate by the log term, let's define a new coordinate v that shifts time by the entire r plus log term. Going back to our light beam equation and subbing in, we get an equation for ingoing light beams that is just the v coordinate being constant. So in these coordinates, the curves of constant v exactly match ingoing light beams. So in Eddington-Finkelstein coordinates, v equals this, and the r coordinate is the same as the Schwarzschild r coordinate. I've labeled the Eddington-Finkelstein r coordinate as Rn, since this is a coordinate system based on ingoing light beams. In Eddington-Finkelstein coordinates, a constant v coordinate labels a specific ingoing light beam, and Rn lets us travel left and right along these light beams, lining up with the Schwarzschild r coordinate on the horizontal axis. So the Eddington-Finkelstein coordinate axes look like this. Let's calculate the metric components for the Eddington-Finkelstein coordinates. Remember, the metric components are just the basis vector dot products. We can get the EF basis vectors for v and Rn from the Schwarzschild basis vectors for CT and r, using multivariable chain rule to expand the vectors. Most of these derivatives are easy to calculate, but this CT over Rn derivative is more difficult. To help compute this, let's introduce an intermediate variable r star, which equals r plus this log term. We can rewrite the v and Rn formulas like this, and rearrange to solve for CT and r. We can show that dr star by drn equals 1 over 1 minus rs over r. Taking the derivatives of these formulas, the v basis vector just equals the CT basis vector. For the Rn basis vector, we can expand the derivative of CT by Rn using the single variable chain rule with r star, since r star only depends on the single variable r. This equals -1, and we solved for this derivative on a previous slide. So we have formulas for the v and Rn basis vectors. Looking at the basis vectors visually, we see that the CT and v basis vectors point in the same direction as we saw before, and the Rn basis vector points in the same direction as the r basis vector, but with an additional negative CT component, so it points downward somewhat. And this is exactly what we need for Rn to point along the direction of light beams. So geometrically, these basis vectors are exactly what we would expect. Calculating Rn.Rn and subbing in the Schwarzschild components gtt and grr, as expected, we get 0, so the Rn direction points along light beams. We also get v.Rn to be -1 and v.v to be the same as ct.ct, since v and ct have the same basis vector. If we were to take the squared length of a tangent vector d by d lambda, traveling in the radial direction, its length would be given by this formula, which contains a cross term with v and Rn because these directions are not orthogonal, and there is no Rn squared term because Rn is light-like with a squared length of 0. We can also plot the outgoing light beams by considering the plus sign of the equation instead. Here, instead of the log parts canceling out, these add together, and the equations for outgoing light beams look similar to what we saw in the Schwarzschild coordinates in Relativity 108b. Note that these light beams are not defined on the event horizon. Plotting on the spacetime diagram, we can see that the light cones rotate as they cross the event horizon. And we can see that any light beams or massive particles that cross into the event horizon can never get back out because of the orientation of these light cones. Now, what I just showed you is called the ingoing EF coordinates, V and Rn, because the coordinate lines match up with ingoing light beams. But we could do a similar trick for outgoing light beams to get the outgoing EF coordinates, U and R out. And we do this by shifting the CT coordinate using subtraction instead of addition. You can check that, using this change of coordinates, outgoing light beams have a constant U coordinate, and ingoing light beams look like this. And note that they are not defined at the event horizon. We get these basis vectors where the U basis vector is the same as the CT basis vector, and the R out basis vector is pointing rightward like the R basis vector, but angled upward because of this plus CT part. For the metric components, R out has a squared length of 0 because it aligns with outgoing light beams. U dot R out is +1, and U has the same length as the CT basis vector. So the formula for the squared length of a tangent vector looks like this, and the two metrics for ingoing and outgoing EF coordinates look like this. For outgoing EF coordinates, light beams on our spacetime diagram look like this, with light cones pointing out of the event horizon. Here, we mysteriously see light beams leaving the event horizon, and all matter in the light cones being forced out of the event horizon as well, unable to return inside. This describes the opposite of a black hole, and so we call it a white hole. So why did the ingoing EF coordinates give us a black hole, and the outgoing EF coordinates give us a white hole? It turns out that the black hole and white hole exist together in space-time, but the EF coordinates only let us see one of them at a time. To understand this, we'll derive a new set of coordinates called the Kruskal-Szekeres Coordinates. So the Eddington-Finkelstein coordinates are nice because they demystify the event horizon and show that light and massive particles can travel through it just fine. But these coordinates still have problems. For the ingoing EF coordinates, outgoing light beams stop working on the event horizon. And for outgoing EF coordinates, incoming light beams stop working on the event horizon. We also saw the mysterious appearance of a white hole for outgoing EF coordinates. It would be nice if we could invent a coordinate system where light beams work in both directions at the same time. This motivates the Kruskal-Szekeres Coordinates, which I'll call KS coordinates for short. In these coordinates, all light beams appear as diagonal lines. The black hole event horizon is also a diagonal line, and the singularity in the black hole center is drawn as a hyperbola. This makes it much more obvious that light can never get out of the event horizon once it enters, because light will always travel parallel to the event horizon, and eventually hit the hyperbola singularity no matter what. So if we want coordinates where light beams work fine in both directions, a first guess is to take the V coordinate from ingoing EF coordinates and the U coordinate from outgoing EF coordinates, and use them together to make a new coordinate system. If we think of time as pointing up and R as pointing right on a space-time diagram, these formulas mix the time and space directions in just the right way so that U and V point along the two light-like directions of the light cone. We can also mix U and V in the right amounts to get back CT and R. And recall, this R plus log term is written as R star for short. You can pause the video if you want to look at the calculations, but we can use the standard procedure for expanding the new basis vectors by using multivariable chain rule. Looking at these basis vectors, we see that v points up and to the right, and u points up and to the left. But there's a problem here. As r approaches the event horizon, the r components get smaller and smaller until the light cone closes up, and the u and v directions overlap on the event horizon. So this new coordinate system still breaks on the event horizon. We can't have a 2D coordinate system where both coordinates point in the same direction. Looking at the metric, as expected, v.v is 0, because v is a light-like direction, and u.u is 0 because u is also light-like. u.v ends up being 1/2 times 1 minus rs over r. The squared length of an arbitrary radial tangent vector becomes this. In most locations, this metric is fine, but again, at r equals rs, this term becomes 0, so the entire upper left square of the metric becomes 0. This tells us that the coordinate lines close over each other, which means that our coordinate system is broken. This single basis vector is light-like with 0 squared length, and light-like vectors are also orthogonal to themselves, so the off-diagonal terms are also 0. The reason our change of coordinates has a problem at the event horizon is this log term, and we need to find a way to get rid of it. The resolution to this is a clever coordinate substitution. First, we'll divide all terms by rs, then exponentiate both sides. We rewrite the exponential sums as products of exponentials, and e and log are inverse functions, so they cancel each other out. I've also introduced a couple negative signs here to prepare us for the clever coordinate substitution, which is big V equals e to the v over 2rs, and big U equals negative e to the negative u over 2rs. Subbing these in, we get minus the product of big V and big U. So this change of coordinates formula no longer has a logarithm term. So we have these coordinate transformations, and we can easily get the inverse transformations just by taking logs to undo the exponentials. Now, since these are single variable coordinate transformations, the directions of the basis vectors aren't actually changing. They're just getting rescaled, so they both still point along light beams and have a squared length of 0. The question is, do we still have the problem where the two basis vectors overlap on the event horizon? To find out, we need to calculate big U dot big V and make sure it doesn't go to 0 on the event horizon. We can take these derivatives, sub in the dot product for small u dot small v, and sub in the big V times big U formula we saw on a previous slide. And after a bunch of algebra, we get that big V dot big U equals this, and this quantity doesn't go to 0 on the event horizon. So these coordinates work everywhere except at the singularity where r equals 0. So the metric with these big V and big U coordinates looks like this, where both the big U and big V directions are light-like and non-orthogonal. And the squared length of a tangent vector looks like this. Now, both big V and big U are light-like directions, and it's a bit hard to interpret what our spacetime diagram looks like using these coordinates. It would be nice to convert these back to coordinates that resemble time and space, which I'll call big T and big X. So before, to get the light-like U and V coordinates, we added or subtracted time and space coordinates. The reverse formulas look like this. So to turn the light-like big V and big U coordinates back into time and space coordinates, we can use a similar relationship, writing them as additions or subtractions of a time coordinate big T and a space coordinate big X. We can once again compute the metric components by expanding the basis vectors using multivariable chain rule. we find the big T metric component is positive 2 times g big U big V, and the big X metric component is negative 2 times g big U big V. You can also check that big T and big X are orthogonal directions. So the metric in big T big X coordinates looks like this. This makes sense, since big T has positive squared length as expected for a time-like coordinate, and big X has negative squared length as expected for a space-like coordinate. And they are orthogonal, so off-diagonal terms go to 0. Also, the squared length of a radial tangent vector in these coordinates looks like this. If we wanted to look at the paths of light beams, we just send this to 0, and to solve this, we find we just need to sub in a diagonal line like t equals plus or minus x plus a constant. Okay, so everything we just did was probably a bit confusing, so let's review. We started with the Schwarzschild time and space coordinates. Then we switched to the light-like u and v coordinates inspired by the Eddington-Finkelstein coordinates. Then we used this rescaling trick to get big V and big U, which are also light-like, but are not broken at the event horizon. Then we converted to big T and big X, which are more similar to ordinary time and space coordinates. These big T and big X coordinates are called the Kruskal-Szekeres Coordinates. Now, it would be useful to have a formula that converts straight from the Schwarzschild coordinates CT and R to the Kruskal-Szekeres coordinates, big T and big X. So we can start with the formulas for big T, then sub in the conversions from big V and big U to the small v and small u. Then we can sub in the formulas from u and v to the Schwarzschild coordinates. Using exponent rules, we can rewrite exponentials of sums to products of exponentials. Note that this rs in front of the log is cancelled by this outer rs. The exponential of a product can be rewritten as repeated exponentiation, so we can put a power of 1/2 up here. Then, since e and log are inverse functions, they cancel, and we just get r over rs minus 1 to the power of 1/2, which is the same thing as a square root. We can then factor the r terms out and get 1/2 times a difference of exponentials involving ct. And you might recognize this as the formula for hyperbolic sine of ct. So this is our formula for converting CT and R into big T. And we can get a similar formula for big X, except it involves a sum of exponentials, and so this becomes hyperbolic cosine instead. So looking at these formulas, they sort of resemble the formulas for Rindler coordinates that we studied back in Relativity 105 for accelerated observers in special relativity. Basically, the space coordinate denotes a series of hyperbolas, and the time coordinate is like a hyperbolic angle that lets us select a location along the hyperbolas. The event horizon is located at r equals rs, which is a hyperbola that's pushed so close to the origin that it becomes a pair of diagonal lines. And again, light beams in ks coordinates are just diagonal lines. Now, the light beams in these coordinates look nice, but this spacetime diagram does look a bit fishy. Why does our spacetime diagram and ingoing light beams stop at the event horizon? And why do outgoing light beams appear to emerge from this other event horizon down here? It turns out that the ks coordinate system is actually composed of 4 spacetime regions. And right now, we're only looking at the first region. We need to go back to our coordinate transformation and think more carefully about this e to the log term. Recall that when we take the square root of a number, we actually get 2 answers. So for example, the square root of 9 can be either +3 or -3. So anytime we take a square root, if we want to list all possible solutions, we need to put a plus or minus sign in front. And when we took the square root of this term, we failed to consider the negative solution. So when we're getting a formula for the big T coordinate, these e to the log terms that we take the square root of actually give us two independent plus or minus signs, which means that the final result involves four possible options: plus sine h, plus cos h, minus sine h, and minus cos h. So we have two independent signs that can be chosen to be either positive or negative, and together these create four possible regions of spacetime, with different combinations of plus and minus sine h and cos h. Also notice that for regions 2 and 4, we're assuming that the value inside the absolute value under the square root sign ends up being negative. Or in other words, we're assuming that r is smaller than the event horizon rs. So we reverse the order of the terms here. Putting all this together, we get four separate coordinate system patches over all of spacetime. For each triangular wedge of the coordinate system, CT travels counterclockwise from negative infinity to positive infinity. In regions 1 and 3, the r-coordinate points outward, and for regions 2 and 4, the r-coordinate points inward. For regions 2 and 4, if we plug in r equals 0, which is the location of the singularity, we get equations for hyperbolas on the upper and lower halves of our spacetime diagram. So in ks coordinates, the singularities are drawn as hyperbolas. The upper singularity represents a black hole, and the lower singularity represents a white hole. As you can see, when looking at outgoing light beams, if a light beam is released inside region 2, which is inside the event horizon of the black hole, the diagonal light beam can never get out into region 1 again, and the light beam is doomed to eventually hit the black hole's hyperbola singularity. For the white hole below, it's the opposite. Any beam of light released inside region 4 can exit the white hole event horizon, which is the diagonal line between regions 1 and 4. But ingoing light beams from region 1 can never get back inside region 4. So the ingoing Eddington-Finkelstein coordinates that we saw before showed us the outer region and the black hole singularity, whereas the outgoing Eddington-Finkelstein coordinates showed us the outer region and the white hole singularity. But the Kruskal-Szekeres coordinates show both singularities at once. Region 3 over here can be thought of as another outer spacetime existing in parallel with region 1, sharing the same black hole and white hole, but with the light beams reversed in direction. These two parallel spacetimes in regions 1 and 3 are connected by a geometry called a wormhole, also called an Einstein-Rosen bridge. In Relativity 108b, we talked about how black holes stretch space itself, so that one unit of the r-coordinate is worth more physical distance as we get closer to the event horizon. We showed that we could embed a two-dimensional spatial slice given by the r and phi coordinates in three-dimensional space, in such a way that the distances we see with our eyes match up with the physical distances near the black hole. Here, the w-coordinate has no physical meaning. It's just an extra coordinate that we use to display distances correctly in our 3D embedding space. The resulting surface is called Flamm's paraboloid. You can derive Flamm's paraboloid by taking the Schwazrschild metric for constant time and theta equals pi over 2 and setting it equal to the 3D embedding space metric, then solving the resulting differential equation. Now, in our Kruskal-Szekeres spacetime diagram, if we look at the constant time ct equals 0, we get one Flamm's paraboloid when approaching the event horizon at the origin from region 1, and another Flamm's paraboloid when approaching the origin from region 3. Putting them together, we get the wormhole, or Einstein-Rosen bridge, connecting regions 1 and 3. However, as seen on our spacetime diagram, light can never travel fast enough to get from region 1 to region 3, or vice versa. So even if the two regions are connected geometrically by a wormhole, no mass or light can actually travel between the regions. As we move forward or backward in time away from the origin, the wormhole pinches off and the two spacetimes in regions 1 and 3 become separate again. So the wormhole geometry only appears for a short amount of time before it collapses, and this period of time is too short for anything to traverse it. That said, Schwarzschild wormholes are not the only type of wormhole, and other wormhole types may end up being traversable. Now, I should mention that the parallel region 3 and the white hole region 4 are mathematical possibilities that exist for eternal black holes, which are theoretical black holes that have existed for all time. But we have never observed white holes or wormholes in real life. For black holes that result from the collapse of a star and whose life has a definite starting point, regions 3 and 4 of this spacetime don't exist. So at this point in time, we have no reason to believe white holes or wormholes exist in our universe, even if they are valid mathematical possibilities that come from the Schwarzschild spacetime geometry. So to summarize this video, we looked at alternative coordinates for Schwarzschild geometry that don't break on the event horizon. By changing to the advanced time coordinate, we were able to pull the ingoing light beams from infinity so that they cross the event horizon just fine. Using these light beams as coordinate lines gives us the ingoing Eddington-Finkelstein coordinates for a black hole. If we shift time using subtraction instead, we get the outgoing Eddington-Finkelstein coordinates for a white hole. Using both ingoing and outgoing light beams as coordinate lines, and using this clever coordinate substitution gives us the Kruskal-Szekeres Coordinates, which show the maximally extended Schwarzschild spacetime, with a black hole, white hole, and two parallel exterior spacetimes. One more coordinate system I didn't talk about is the Penrose diagram. You can check the links in the description to learn more about it.